Now, the example that we want to consider is simple enough, yet it will help us appreciate some of the major issues that we have to think about when we have thermal loads. So the example consists of a rigid surface. Surface is rigid and it is frictionless. Okay. So additionally, what we have is a upper surface. Let us draw that in again. Black. So we have a upper surface. I'm going to identify this also as being a rigid bar. Okay. And between the rigid bar and the rigid surface, we put cylinders. And the rigid bar, by the way, it's also frictionless. And we're going to put 3 metallic bars in between. Remember, there is nothing that is physically rigid. It's just something that we can omit the deformations of. Okay, so in this case, it's safe to omit the deformations of the rigid of the bar at the top and the surface at the bottom. So we have a 2 cylindrical structures, solid cross sections, and yet another one in the middle. The one in the middle is aluminum, and the other 2 are steel. Okay. All right. Then we know the dimensions, that they are cylindrical and the diameters are respectively 40 millimeters. This one as well, they're identical, 40 millimeters. This one over here, it is 60 millimeters. And on top of this, what we are going to ultimately do is impose a distributed load of uniform magnitude, and that load is going to be, okay, so this, let's say, is sort of the center, and the load is going to be distributed in that fashion. Okay, onto the rigid bar. And the load has a magnitude of 150 kilonewtons per meter. Okay, it's going to be applied to the rigid bar. I've drawn it a little bit far from the rigid bar so that in our future discussions I can easily sort of imagine that it's not there. Okay, and these distances are, they're symmetric. This is 300 millimeters. This as well. Okay, good. We do need material properties. So first of all, and importantly, we have the mechanical load as well as a thermal load, which says that the temperature starts from some initial value, goes to some final value. In this case, that's indicated by T1, and the initial value is equal to 20 degrees Celsius. The final value is 80 degrees Celsius, which means that our temperature change is positive and it is 60 degrees Celsius. Then the material parameters are the Young's modulus of steel. We know order of magnitude wise 200 GPa, and the Young's modulus of aluminum, again, we know 73. Let's say I stick to the example, take it to be 73.1. And we need also the coefficients of thermal expansion. So that is a new parameter for us. So alpha of steel and alpha of aluminum, they are needed. And they are both of the order of 10 to the minus 6 times 10. So that's sort of in the upper range. Remember, 1 to 10, 10 to the minus 6, 1 over degrees Celsius is the range for these parameters. It doesn't mean that the max is 10. It's of the order of 10. So 23 and 12, they are also of the order of 10. All right, good. So that's all I need to solve ultimately my problem. And the question is, find the force in each bar. Okay, that's the question that we want to answer. All right, so now a couple of remarks regarding the setup. So we have two blocks resting on the rigid surface, and I'm going to load it through this rigid bar. It just acts as a medium to transmit the load that I'm going to apply, and simultaneously I'm going to imagine the following, that the bars, each bar is constrained from getting detached from the rigid bar and the rigid surface. So each cylinder is stuck to the surface it's in contact with. So in other words, if I pull on this bar, it's not gonna just lose contact. It's gonna pull the cylinders along with it, right? But in doing so, and the same thing for the rigid surface, if I were to displace it down, it would pull on the cylinders. And on the other hand, they are frictionless. So in other words, the cylinders are free to expand or contract without displaying a stress in the third direction. So it's intrinsically a 1D scenario. These are, if you like, strong magnets. You can pull on the metals, but the metals can also slide freely on the magnets. Okay, all right, good. So that's our scenario. So there's a good connection between, and let me indicate that with these green lines, if you like. So, okay, so the interface is connected. Good. So now let's go ahead and think about the problem. Now, first, we have to agree on a number of cases. Case number one, if I were to only push on the rigid bar without any temperature changes, what would be, let's think just about the state of the force, whether it's tensile or compressive. What would be the state of the force in each cylinder? Well, we can immediately see that if there is only the green mechanical load, then the state of loading is going to be compressive. And if it were tensile, then each one would be tensile. So that's easy. What is not quite easy is to determine the amount, the magnitude of the force in each bar. I know that it's compressive when in this scenario without temperature change, but what is the magnitude? Now, in this case, you can remember that the situation is governed by a setting where you are trying to find two forces. These are going to be equal. That's why we impose symmetry. So ultimately, some of the forces in the horizontal and out of plane directions, they are not of concern. This is an ultimately one-dimensional scenario. And therefore, equilibrium requires some of the forces along that direction is equal to 0. The moment about any point within the plane is automatically 0 because, again, these forces will always be the same. And so it will, due to the symmetry of the distances, 300, 300, the moment equilibrium is automatically satisfied. So the only equilibrium equation I have eventually is some of the forces along the axis of the cylinders is 0, but I have two forces, one equation, two unknowns. Okay, so remember what you do in that scenario. So that's a good way, also good opportunity to recall the ME 231 content. Take a few seconds. How would you generate an additional equation for the two equations? We presently only have one, equilibrium. Okay. So now the answer is, of course, compatibility, namely that everything is going to elongate, in this case, get compressed by the same amount due to the constraints that we are imposing. Right? So compatibility generates an additional equation And so you have now equilibrium and compatibility for the two unknowns, the forces in the bars. And the forces are qualitatively, at least I know they're compressive. I don't need to solve anything for that. So suppose now there is no bar. If there is no bar and we just change the temperature, how do the strains because the initial lengths are all the same, and let me provide you with that as well because I forgot. The initial length of the bars, it's 250 millimeters. So because the initial lengths are the same, they're going to elongate by the same amount. So the strains are, well, they may or may not elongate by the same amount, but the initial lengths are the same. So instead of comparing the elongations, I can always compare the strains. So if there is no bar, so the upper surfaces are free surfaces, presently they're not. If they are free surfaces, if I change the temperature in this fashion, how would the strains or equivalently elongations compare? Well, at this point we just remember the concept of thermal expansion. Whatever has a larger thermal expansion coefficient is going to expand more, and therefore the answer is the aluminum. So the red cylinder is going to expand more, it's going to elongate more. Okay, so pure mechanical loading, I understand what happens in the presence of the rigid bar. If there is no rigid bar and if I have pure thermal loading, I understand what happens. Cylinder expands more than steel, it also expands. Next question, if there is no rigid bar, same thing, and you just change the temperature and aluminum expands more, it elongates more, what is the generated stress in aluminum or steel? The answer is 0, because I just assume that there is no bar and there is no loading therefore, and these are now upper surfaces are free. You get a strain, but that strain is not from mechanical loading, it's from thermal loading. And so the fact that you have strain, remember, doesn't mean that you have a load applied to it. You can have 0 load, yet a certain amount of strain because of the thermal contribution to the overall strain. Okay, so that was the concept that I told you we have to free ourselves of, right? The generalized Hooke's law, in the case of thermal elasticity, combines several effects together. Okay, so, all right, good. Now let me ask you yet another question. Suppose again that you don't have this load, but you do have the rigid bar. And we change the temperature. So the bar is there, it is connected to the cylinders are connected to the rigid surface, and you change the temperature. And now the question is, what are the forces qualitatively in each cylinder? This is something, not quantitatively, just qualitatively, we can easily deduce from the values of material parameters we have. So take a few minutes. So the answer is going to be the following. It's either gonna be, say, all tension or all compression, or one under tension, the other in compression, and I don't know which one, okay? So there are several possibilities, but I'm just asking for a qualitative assessment of the situation, okay? So what is the answer? If we have this scenario and if the temperature increases by 60 degrees Celsius, will all the cylinders be in tension? Will all of them be under compression? Or will some of them be under tension and some of them be under compression? And if so, which one is under tension? Okay, think about that question for a second. And now I can continue if you pause long enough. Well, first of all, what is the guiding principle deciding whether it's all tension compression or some is under tension, the other is in compression? Well, it's the concept again of equilibrium. The rigid bar itself, if I draw its free body diagram, there is no load applied from the top. The green loading is not there. And if any load is imposed on the rigid bar, then it's going to be due to the cylinders. And no load is going to be imposed on the rigid bar if all the materials were the same, because then they would expand by exactly the same amount and this bar would try to move up uniformly. In any case, it will move up uniformly, but it would do so without any force being imposed on it, because this expands, that expands, that expands exactly by the same amount. Because the expansions are the same, the expansion of each one is not meeting any resistance, and therefore no force is generated. So if all were steel or aluminum, you can see eventually that first of all, due to equilibrium, some of the forces in any case have to be equal to zero, no force on the rigid bar. But if the thermal expansion coefficients were the same, then the individual forces in the cylinders would also be zero. But the thermal expansion coefficients are not equal. Aluminum tries to expand more. And so aluminum tries to expand more, and you can physically think that as it does so, it tries to make the blue cylinders, the steel, expand along with it, but conversely, steel doesn't want to expand that much, so it's going to pull back on the aluminum. So aluminum is going to go under compression, and steel is going to go under tension. Okay? So let me give you another way to think about that problem. So I'm going to write here only delta T. If we have only delta T, then we have a situation where we have just a quick sketch. We have initial lengths of the cylinders. I'm just drawing lines on the surface, and the rigid bar is there. But what I'm going to do now is I'm going to apply sort of a superposition principle. First, I imagine that I only change the temperature without the presence of a rigid bar. So the aluminum will try to expand more, but steel will try to expand less. Okay? So this is the original position of the cylinders. And now red is more, blue is less, experiences less of an expansion. So now I put the rigid bar back there, and what the rigid bar tries to do is it tries to bring everything to the same level because it needs to remain straight and it's rigid, and therefore the rigid bar is going to go somewhere in between. So it's going to pull on the red, it's going to push on the red and pull on the blue to make them come to the same level. So blue is going to be under tension and red is going to be under compression. So if we have only delta T, what we expect is that aluminum is going to be under compression and steel is going to be under tension. So TCT is what I'm writing just to remind ourselves of this hypothetical scenario. Okay. So now what we have found out that if we have only the green load, there is no temperature change. Everything goes under compression because I'm pressing on the bar. The bar will move down, make everything go under compression. Okay? And what we've deduced is that if there is only temperature change with the same scenario, with the bar being there, the aluminum is going to be under compression, steel is going to be under tension. So now, what we have is a situation where both the temperature change and the load is there. So presently, therefore, what we ultimately can immediately decide is that when we have both effects present at the same time, in other words, we have a sum of the problems, qualitatively, the solution is going to be sum of the solutions, and therefore I can already deduce that aluminum will certainly be under compression. Okay. So in our combined setting, aluminum has to be under compression, but I don't know what happens for steel because I don't know whether the compression due to the load or the tension due to the temperature change will dominate. If the temperature change effect dominates, the tensile effect will be larger than compression. This will be tensile. If the load dominates, it will be compression. So, and to determine that, I have to solve my problem. But you see, we always highlight that we should judge the result qualitatively to see whether it makes sense or not. It doesn't mean that our result is correct, but just to judge whether it makes sense or not. And now I know that at least eventually when I find a result, and if aluminum comes out to be tension, I can immediately suspect something. I must have made a mistake. So it's going to at least guide my calculations to a certain extent. And moreover, we're now building some intuition how to solve this problem. So now let's go ahead and actually solve the problem in detail. So first of all, the first thing we're going to do is we're going to draw the free body diagram of the bar. And the free body diagram consists of the net force that I am applying on the bar, which is 150 kilonewtons per meter times 0.3 meters, which is therefore simply 90 kilonewtons. Okay, and we will have forces within the aluminum and steel bars. Now, here, let us be careful. I'm going to indicate that those forces in a slightly non-conventional fashion. So first of all, remember that the bars themselves are over here. So here is the bar. Okay. I'm not drawing the whole bar. Sorry, this should have been red. Okay. And then there is the other aluminum bar. Now, I know that the aluminum bar needs to be under compression. So in other words, the force direction should be like this. So the force acting on the bar is equal and opposite. So I will immediately go ahead and write it as such. So this is force on aluminum. Okay? That is based on my expectation, but I don't need to rely on my expectation. I could have chosen the force in the other direction as well, right? Remember, that's just a matter of convention. But that means that if it comes out to be positive in this case, it is indeed compression, and therefore it has to come out to be positive. That's my definite expectation. But if I had chosen the default direction of the force in the other direction, then the result would have been negative because it indicates that it was the wrong direction. So the sign indicates whether my assumption was correct or not. So now, how about the steel, forces on steel? I don't know in which direction they have to come out to be. I'm going to assume that they come out to be in that direction. Okay. Now, I have no expectation on the bars, so whether they're tensile or compressive. If they come out to be positive, it means they were also under compression, certainly plausible. But if they're negative, it means it was wrong, my assumption. I should have assumed they were in the other direction. So if they were in the other direction, it means I'm pulling on the bar. Okay, so this picture down here is just a way to keep the direction of the conventions more clearly in mind. Okay, so the forces are acting on the bars. The force acting on the cylinder is in the other direction. Okay, do not be confused by the proximity of the cylinders to the forces. Okay, so now that is my free body diagram. I am concentrating on this free body diagram, this portion. The forces act on the bar, not on the cylinders. The direction is reverse for the cylinders. And therefore, some of the forces in that direction, let's take that direction to be positive, should be equal to 0, which means that 2 times steel plus force on aluminum needs to be equal to 90 kilonewtons. Okay, or those minus 90 is equal to 0. Okay, equivalently. So this is my equilibrium. Now, equilibrium gives me one equation, but I have 2 unknowns. Now, as we mentioned before, I need another equation, and that equation comes from compatibility. And compatibility, in this case, says that the amount of elongation of steel is equal to the amount of elongation of aluminum cylinder due to the geometry and due to the rigid bar assumption And that allows me to ultimately generate one additional equation in terms of the forces I'm seeking. The forces are eventually the unknowns in my system. And two equations, two unknowns, ultimately I can determine the answer, right? Now, the reason I'm emphasizing all of this, which is 231 knowledge, so that you again recall the importance of ME 231 in the context of this course. And if you feel uncomfortable, it's a good opportunity to go back, recall by solving some additional problems. So presently, elongation is change in length over initial length, but presently the length is the same for all cylinders, and therefore this is the same as saying that the strain in aluminum is the same as strain in steel. And now at this point, we go ahead and apply the generalized Hooke's law in 1D. Okay? Now in 1D, first of all, the strain is always, in a thermoelastic loading, going to have a contribution from the thermal temperature change, alpha delta T, and that contribution here is going to be alpha aluminum delta T. Plus, however, there is going to be an additional contribution from the stress, and that stress is 1 over the Young's modulus of steel times the stress in steel. That stress is along the axial direction. There is no Poisson effect because it's an intrinsically 1D scenario, because these are frictionless, sort of acting like magnets, right? So this is 1 over aluminum, consequently the stress on aluminum. Good. So, well, then we need to remember, and this is where a second level of, let me say, care is needed. Now we need to now write the stresses in terms of the forces. Now the stresses are, they are force over area. So the stress is the load on aluminum, or the stress on steel is the load on steel divided by the area of steel. The area is associated with that diameter, and therefore this is also force over area of aluminum. Good. Now, I am not trying to trick you, but at the same time trying to trick you. So, is this correct is my question. The green expressions are correct. Just to make you focus, is stress steel equal to that, and stress aluminum, is it equal to that? Think about that for a second. Okay? The answer has to do with the sign of the stress. So, remember that the generalized Hooke's law, or for that matter, the relation between stress and strain, it works with the signs inside. It's not working in a qualitative fashion with its compressive, its tensile, etc. Because we have physical parameters that tell us that you will get a positive strain if delta T is positive, and negative strain if delta T is negative. So the signs are embedded in the values themselves of the quantities. And therefore, this stress, to predict the correct amount of strain, also will need to have exactly the correct sign. If you don't put the correct sign, you're not going to get the correct value. So presently, by default, I have already assumed, notice, that the force on every force component on each cylinder is by default compressive. Okay? If F greater than 0 in this case, then compressive. Now, if the force is compressive, the resulting stresses have to be also indicating compressive stresses, and therefore I need to have a minus sign, because that's positive whether it's tension or compression, right? Or in fact, it is already compression, and qualitatively I know that's compression, so quantitatively I need to go ahead and plug in that minus sign in there so that the stress actually is negative. So this is what we have observed before, this is what we're observing now, we're going to observe it again. You always have to use the stress in the generalized Hooke's law, with or without thermal loading, with the correct sign. Otherwise you'll end up having wrong answers. So the correct expression for the stresses in both cases is with the minus sign. if I had assumed that all the forces were in the other direction, in other words, they were by default tensile, I wouldn't need to put these minus signs in there, right? Okay, so now, therefore, I have one equation in terms of forces, another equation in terms of forces. Why is this another equation? So that's my equation number 1. This is my equation number 2. Well, because the Young's moduli are known, the areas are known, the temperature change and the coefficients of thermal expansion are known, and so now I can go ahead and solve for the problem and determine that the force in aluminum, well, what shall it come out to be? Positive or negative? I already know that it has to come out to be positive because I know it has to be in a state of compression, and by default I chose it to be compressive. So indeed it comes out to be under compression, 123 kilonewtons. Okay, so that is C, and that checks. That is indeed what I was expecting. Now then the force in steel comes out to be on the other end negative. So it comes out to be negative 16.5 kilonewtons. Okay, so in other words, it is negative 16.5 kilonewtons compression, which is weird to say. It is really 16.5 kilonewtons tension. So I was wrong with the direction of the blue force, should have been pointing down, but the sign is already an indication of that. And you see, now going back to the beginning of my analysis, what turned out to be is that the temperature change, okay, so let's write that here. So it should be 16.5 kilonewtons tension. What turned out to be is that the temperature change effect is so large that it dominates the compression effect due to the mechanical load, and the thermal load is ultimately responsible for deriving the overall force in the steel to the tensile range, and that's what we have observed here. So this was a very good, nice example, putting together several concepts together in the context of essentially a 1D setting, but eventually in the homework problems you'll have a chance to consider three-dimensional thermomechanical loadings.